Hi, my name is Sarah Jones. I'm a PhD student with Dr. Danny Singh in the soybean breeding lab. Drought is one of the major yield constraints in crop production, and its patterns can be traced globally in worldwide yield losses. Because of this, and because of some recent studies that have come out showing that North American soybean may be at a high risk for low yields associated with drought due to the timings of drought, it's important that soybean breeders are developing varieties that can withstand periods of drought to increase farm profitability and food production. We focus on two methods in our lab, phenotyping and genetics, to improve drought-tolerant soybean varieties. Traditionally, we would visually look through a field of lines and select the ones that have the least drought symptoms and better plant health in comparison to checks. But now with drones and cameras that have a range farther than visual, we can collect more information, and this can help us identify genetic sources of drought tolerance that we can then incorporate into the breeding program.
Hi, I'm Timley Ayalade, PhD student working with Dr. Shomik Sakar in the Department of Mechanical Engineering. Combining the data that we collected from multiple sensors, including the thermal sensor, the multispectral sensor, RGB sensors, all collected on the drones, the hyperspectral sensor, and the vegetative indices, we had over 2,000 variables which were helpful to accessing the drought conditions on the field. But this is too much data and very difficult to work with in real time. So we use machine learning methods to build a pipeline that can use all this information and make drought stress classifications similar to what an expert trader will do on the field. In addition, we also select the most important information, the most important variables, the most important sensors that are useful for drought stress classification for plant breeders. Bringing this together, we've developed a pipeline that can help automate phenotyping over thousands of experimental lines, making this efficient and also improving the accuracy. We use machine learning methods to take advantage of the visible and non-visible spectral information. Using this information, we're able to detect drought stress in crops even before they become visible to the human eye. In this way, we can identify which soybean lines were beginning to show stress prior to the visual symptom development. With early detection done like this, a farmer can act to quickly determine the cause and mitigate that stress.
We take the most valuable sensor data that was selected by the machine learning pipeline, combine this with our experienced rater data, as well as genetic information. And combining all of this information, we can find patterns and associations between the genetic information and the sensor information. This helps us identify genes that are specifically related to drought tolerance that can then be incorporated into the breeding program. We can apply these selected sensors for more efficient phenotyping of large populations of soybean in the field to detect drought tolerance and advance improved lines. We hope that these technologies will become available to breeders so that they can breed improved crops and improved drought tolerant crops for farmers.